Hey guys, my name is IBM and I'm still taking you through waves and superposition. I think this is going to be lesson 9. Before doing that, I would like to always remind you of the course outline of the AS Physics syllabus. Not forget to watch the solved past paper questions of all these topics. However, you should first study the concepts of physical quantities and units, errors and uncertainties, treatment of uncertainties, kinematics, dynamics, force, density and pressure, work, energy and power, deformation of solids, waves and superposition, electricity and DC circuits, particle physics. And I said all the units in red have already been recorded and each of them has its own playlists. Currently, we are dealing with waves and superposition, and this is going to be lesson 9, where we shall still be dealing with standing waves or stationary waves. And this time, we shall be concentrating on stationary waves in pipes. Okay, so we are continuing the superposition, and remember, we have to study standing or stationary waves, diffraction of waves, and we have to study interference and the diffraction grating. The order of these units may not be the same order that your teacher may be teaching them, but I just put them in this order for my own convenience. And I think this is lesson 9, as I have already said, and we are going to talk about basically stationary waves in pipes, because you have seen several musical instruments or several instruments that produce sound by just simply blowing in air into the pipes or into pipe-like instruments such as the flute. So let's talk about stationary waves or formation of stationary waves in air. So the figure above here shows an experiment which is used to demonstrate a formation of stationary waves in air. Even in air, stationary waves can be formed. And what is happening with this figure is that a fine powder, such as lycopodium, has been sprinkled evenly all over the surface, all over the bottom of this transparent tube before putting a sound signal, or before putting the loudspeaker close to the open end of this pipe. So a fine powder, which is most likely going to be lycopodium powder, is sprinkled evenly along the transparent tube, and when a loudspeaker powered by a signal generator is placed at the open end. So of course, for a signal generator, the frequency of the signal can easily be altered or changed, increased or decreased, and the loudness can also be increased or decreased easily with a signal generator. So loudspeaker powered by a signal generator is placed at the open end, and the frequency of the sound from the loudspeaker is gradually increased. So what happens is that at certain frequencies, we now see the powder, or you would see the powder forming heaps, which heaps are evenly spaced along the tube. So at certain frequencies, the powder forms itself into evenly spaced or equally spaced heaps along the tube. So what is really happening? Why do we have equally spaced heaps along the tube? What is really happening? So it means a stationary wave has been set up in the air which is inside the tube. So the wave is caused by the interference of the sound wave which is coming from the loudspeaker and the wave reflected from the closed end of the tube. So a continuous wave which is coming from the loudspeaker moving to the other end, maybe to the right hand side, meets a wave which is being reflected from the closed end from the right hand side to the left hand side. And when the two waves meet at a point, or when the two waves continuously meet, this results into points where particles will be permanently at rest, which we shall call destructive interference later on, and the points where particles vibrate with the maximum amplitude, which we shall call points of constructive interference, resulting into nodes and antinodes. So of course we know that at a node, as we have already mentioned, there is zero amplitude, there is no disturbance at all, and the powder can settle into heaps. So the reason as to why we have evenly spaced heaps It's because the powder there's almost no disturbance at these points, and therefore the powder can settle in heaps, resulting into nodes. And at points where there's completely no powder, then the disturbance is maximum. That means the air molecules in those points are vibrating with maximum amplitude, and therefore this results into what we call the antinodes. So at the antinodes, the disturbance is at a maximum, and the powder is dispersed away. That's why why we see a continuous series of antinodes, and nodes along the tube. So what has been set up is a stationary wave. A progressive wave coming from the loudspeaker propagates from the left-hand side to the right-hand side. It undergoes reflection. But because there's a continuous progressive wave coming from the loudspeaker, then the incident wave from the loudspeaker and the reflected wave from the other end meet at a point. These two waves are going to be of the same type, moving at the same speed, but in opposite directions. They have the same amplitude, and when they undergo interference, or when they undergo what we call superposition, they result into nodes and antinodes. Therefore, we say a stationary wave has been formed. A stationary wave has been formed. So a stationary wave can be formed in air. Waves in pipes, or let's talk about the vibrating air columns in more details. So we have seen already that a stationary wave can be formed in air. So in a vibrating air column, stationary waves are set up as we have seen with a pipe. And these are the sources of sound in most wind instruments like the flute. So the stationary waves which are set up in air are the sources of sound in most of these sound instruments that use wind as as their source of sound. So wind instruments consist of pipes which may be closed at one end and open at the other end, or open at both sides. So we shall call those which are closed at one end, we shall call them closed pipes, and those which are open at both ends, we shall call them open pipes. So by blowing air, or by blowing at the open end, a progressive sound wave travels to the end of the pipe where it is reflected so that it comes back to the end where it was produced. Of course, the incident and reflected waves have the same amplitude, frequency, and speed, but they are only moving in opposite directions. Of course, they have the same amplitude because when a progressive wave reaches the other end, it is just reversed without changing the amplitude, it just changes direction so that it moves now in the opposite direction. So the incident and reflected waves have the same amplitude, same frequency, and they have the same speed because they're even of the same type. The only difference is that they are moving in opposite directions. So when the incident and the reflected progressive wave superpose or meet at a point, they produce what we are now calling stationary waves. So that is how stationary waves are formed in pipes, or that is how stationary waves are formed in air due to air columns in pipes. So like we have seen stationary waves formed on strings, we are now going to investigate stationary waves formed on pipes, only that we shall now distinguish these two into both uh, closed and open pipes. So let's start with the closed pipe. So which modes of vibration exist in a closed pipe? We saw the modes of vibration which existed on a string, and we derived an expression for the frequencies or the possible frequencies which result into stationary waves. Remember, the major difference between stationary waves and progressive waves was that even though for stationary waves no energy transfer occurs, for progressive waves there was energy transfer. And number two, there were specific frequencies for which stationary waves were formed, which was not the case for progressive waves. So even here, in a closed pipe, there are specific frequencies for which stationary waves are formed. Remember, when we hear a loud sound, we say resonance has occurred because the amplitude is going to be higher. And of course, amplitude relates to loudness if we are talking about sound. So we say resonance has occurred, and that frequency, we call it resonant frequency. So there are specific resonant frequencies in pipes, and we shall call them the modes of vibration. So a closed pipe is the one which is closed at one end. It is not closed at both ends, even though we are calling it a closed pipe, but it is closed at one end. And when a blast of air is blown at the open end of the pipe, a progressive wave travels down the pipe to the closed end where it is reflected. The most important thing here is getting a wave which moves in the opposite direction. It is only being achieved here by reflection. So a progressive wave moving, say, from left to right undergoes reflection on the other closed end of the pipe. The incident and the reflected waves have the same speed, same amplitude and frequency, but moving in opposite directions. When the two waves superpose, or when the two waves meet at a point, stationary wave is obtained. So every time I'm explaining how a stationary wave is formed, I'm talking about the incident and the reflected wave. These having the same speed, amplitude, frequency. In other words, they are of the same kind. However, they are moving in opposite directions, and they must be superposing. They must be meeting at a point. That is how a stationary wave is formed. So the stationary wave obtained is such that a displacement node is formed at the closed end, while a displacement antinode is formed at the open end. So when a stationary wave is formed in a closed pipe, we always expect an antinode at the open end. Why? Because at the open end, there's less pressure, so the air molecules can easily vibrate with maximum amplitude. Yet at the closed end, there is more pressure because the air is concealed in a small, the air is forced in a small point or in a single point. Therefore, there is no free space for the air molecules to vibrate easily. Therefore, we always expect a node at the closed end of a closed pipe. So this is because air at the open end is free to vibrate and so vibrates with the maximum amplitude, resulting into an antinode. So we always expect an antinode at the open end. So that is a point of minimum pressure. An antinode is a point where there is minimum pressure. The particles are free to vibrate because the pressure is small or is minimum. But then on the closed end, on the other end, the closed end, the air isn't free to vibrate and is therefore permanently at rest, giving rise to a node or a point of maximum pressure. So it's like a node is corresponding to a point of maximum pressure. In other words, where air molecules or air particles are under maximum pressure, and an antinode is corresponding to a point where the air particles are under minimum pressure, so they are free to vibrate with maximum amplitude. So I can summarize this with a simple animation. So in this animation, this is a closed pipe, and the air molecules on this open end here have enough room for them to easily vibrate, resulting into the formation of what we are going to call an antinode on the open end. At the closed end, the air molecules are under maximum pressure, they are under high pressure, so they cannot easily vibrate. They cannot easily vibrate. So we always expect a node at the closed end. So of course we may have varying nodes and antinodes depending on the length of the pipe. So the open end corresponds to minimum pressure, but of course it corresponds the particles they are vibrating with the maximum displacement. That's why maximum amplitude. That's why you see the displacement graph shows when the pressure is zero at the open end. I think I should change this to a pen. So the displacement end corresponds, you notice that here at the open end, the pressure is already zero. Let me draw a horizontal line through this. And I'll also draw a horizontal line here. So I want you to notice that for the closed end, where we have, for the open end where we have the amplitude, the pressure is always at zero. That means the pressure is minimum at the open end where we have antinodes, or where we have an antinode. And there the particles always vibrate with the highest or the maximum amplitude. That's why you see the amplitude goes to maximum the other side and this side down here. Then somewhere here, for example, at this point here, again the particles are also vibrating with this point is always also at the same point, so always at minimum pressure. So the particles there also have zero amplitude because the pressure, I have maximum zero pressure because uh, there is an antinoid which is being formed somewhere there, and therefore the particles there, if we consider the graph of displacement, you notice that the amplitude of displacement, the amplitude of vibration is also greater in this region here. But somewhere here, where the pressure is always maximum, you notice that the graph for pressure is always going to a maximum value around this point here. In this region where the pressure is maximum, the amplitude is always zero. That's if I join all these three diagrams. At this point here where the pressure is always maximum, the amplitude is always going to be zero. That's why you see this point is always remaining at the same position, at the equilibrium position. So it means the open end equals to the open end we explain a pressure, we experience or we expect a pressure node. When we talk about a pressure node, that is minimum pressure. Minimum pressure, but it is a displacement antinode. That's why you see the graph of antinode amplitude is showing a maximum amplitude here. And at the closed end, we expect a pressure antinode. When I talk about a pressure antinode, I'm referring to maximum, the point where we have maximum pressure. The particles at the closed end experience maximum pressure. They are overcompressed at that point. But of course, if the pressure is maximum, we notice that the amplitude remains zero at that point. So corresponds to a displacement node. That is for a closed pipe. So each pressure node is a displacement antinode. This is a very important statement. Whenever you see a pressure node, it corresponds to a displacement antinode. In other words, whenever the pressure is zero, the displacement is maximum, the displacement is the highest. And whenever the pressure is maximum at a given point, the amplitude of vibration is going to be zero. That's why we say each pressure antinode is a displacement node. And that is very, very, very important. So this animation, it should give you a clear link between pressure at a given point and the displacement of the particles or the amplitude of the particles at that point. And we are saying for a closed pipe, at the closed ends, for a closed pipe at the closed end, we expect the pressure to be high, so the particles cannot easily vibrate. So if they can't easily vibrate, that means the amplitude is going to be zero. That's why we are calling that a node. And at the open end, the pressure is low because the particles are free to vibrate easily. And because the particles are free to vibrate, the pressure is low. And this means the particles can have maximum amplitude or the highest amplitude. That's why we have a displacement antinode at the open end. That is for the open pipe. So let's talk about the modes in details as we saw with a string. Let's begin with the first harmonic or the fundamental mode of vibration. Now we already know what to mean by first harmonic or fundamental mode of vibration, but this time we are going to use it on a closed pipe. So we have seen a simple demonstration or simple animation of a closed pipe, where particles at the open end are free to vibrate easily, therefore they vibrate with maximum amplitude. In other words, they vibrate to bigger distances. Now, these lines here are showing how particles vibrate, and you notice that the length of the lines decreases as you move towards the closed end. So, one, remember sound is a longitudinal wave. Therefore, the vibrations of particles are parallel to the direction of to the direction of propagation of energy. If a wave is propagating from the top to the bottom, the particles vibrate parallel. That's why I've drawn these lines parallel to the axis of the pipe. Otherwise, I would have drawn them like this. So this would be the correct way of drawing the orientation of the particles, or how particles can be represented in a pipe, or air vibrations can be represented in a pipe when the sound is propagating from the open end to the closed end. So the length of this line, these lines, is showing that the vibrations, or the amplitude of vibration, decreases as you move towards the closed end, because the pressure the pressure increases to the closed end. So of course, for learning purposes, we shall always represent this by this, although this gives people an impression as if the particles are vibrating like this, but that is not true. The vibrations are always parallel to the axis of transmission. The vibrations of the particles are parallel to the axis of transmission, like this. So the length of these lines should just be reducing as we move towards the closed end, and so on and so forth. So at the open end, the amplitude of vibration of the air molecules is maximum. That's why we are saying at the open end we have a node. At the closed end, at this point there is no vibration of the air molecules. So at this point we always expect at the open end we have an antinode. At the closed end we expect a node. So this figure shows the simplest mode of vibration. In this mode, you notice that this is a quarter. I think this is a quarter of a cycle, because if it was a half a cycle, it would be something like this, because a full cycle would be something like this. A full cycle is something like this. Now if I put an envelope the other side, then I cut off 1/4, so this is a quarter of a cycle. So this is a representation of a quarter of a cycle. So the figure shows the simplest way in which the air in a pipe closed at one end vibrates. The simplest mode of vibration. So figure A is showing how the particles vibrate. So it illustrates the motion of some of the air particles in the tube. And their amplitude, as I've indicated, the amplitude of vibration is 0 at the closed end, and it increases with the distance up the tube at a maximum at the open end. So the length of these lines is showing how the amplitude changes, and it is maximum at the open end. Then figure B is what we use for convenience. So figure B is just the conventional way of showing the amplitude of vibration. The amplitude along the axis of the tube are plotted as a continuous curve. One danger of using this illustration here, one danger of using this diagram, the diagram like that in B, is that they give the impression that the sound wave is transverse rather than longitudinal. So you must be very, very careful when you are dealing with the pipes, and you have shown this. I said people would think when I draw such a diagram and I say the open end amplitude is maximum, people would think that the particles are actually vibrating like this. But like I said, the particles, because this is sound wave which is longitudinal, the particles vibrate parallel to the direction of propagation of the wave energy. If the wave is moving from up to the bottom because wind is blown from the top, then the air particles must also be vibrating parallel to the axis of transmission, not perpendicular to the axis of the pipe. Okay, so let's derive the fundamental mode of vibration of a closed pipe. So, like I said, this is a quarter of a cycle. So because this is a quarter of a cycle, I want you to see how the particles, this animation demonstrates how the particles behave. For a fundamental mode of vibration, the particles this side do not easily vibrate. As you can see, the lines are almost not moving. That's why I said we expect a node here. That is a displacement node. The particles here vibrate with maximum amplitude, as you can see. That's why we said we expect an antinode at the open end. And this line here, which is moving, is actually an equivalent to what I have drawn here. If I was just to trace this out to show how the particles So this is equivalent to what I've just illustrated here, showing how the particles vibrate. But note that the movement of the particles is along the axis of transmission, because the wave moves, if the wave is moving in that direction, the particles are moving to and fro, parallel to the direction of propagation of energy. So they are the particles vibrate parallel to the axis of transmission. So because this is a quarter a cycle, then I would say that L equals to a quarter of a wavelength. So which means the wavelength is going to be 4 times L. So if I try to find a frequency in this case, which is going to be the first harmonic, which is also going to be the fundamental mode of vibration, is going to be V divided by lambda, which is going to be equal to V over lambda, which is 4L. So it's like the fundamental frequency F naught which is the same as FL, is V over 4L for a closed pipe. So the distance L is the distance between the node and the antinode, and L is equal to a quarter of a wavelength, where lambda is going to be 4L. So when I try to find a frequency, the frequency is going to be equal to to V over 4L. And since this is the fundamental mode, and the fundamental mode is the first harmonic, so it means F1 and F0 are the same, which is simply going to be equal to V over 4L, where V is going to be the speed of the sound in air. So that is what we call the first harmonic, or the fundamental mode of vibration. Then let's see what happens. Suppose we increase the frequency here slightly higher. Suppose we increase the frequency slightly higher. The next frequency above this involves introducing a node. Unfortunately, when we introduce a node, an automatic antinode is created. In the process of introducing a node to increase the frequency, an automatic antinode is always created. You notice that the number of nodes, we have one node, we also have one antinode for a closed pipe. I want you to mark that very carefully. So let's think of a situation where the frequency is increased to have what we call the first overtone. Remember, an overtone is a frequency higher than the fundamental. So unfortunately, when we try to increase the frequency to create a new node, we end up creating another antinode, as we can see in this animation here. So we have now created another node, but in the process, we have come up with another antinode. So this is what is happening here. We have increased the frequency, but what in the process of increasing the frequency, or in the process of creating another node, another antinode is going to be created, because we cannot have a node at the open end. We shall always have an antinode. So therefore, it means what is happening is actually something like this. So in open pipes, or in pipes, overtones are produced by blowing harder. So to increase frequency, you can even blow harder at the open end. So if we blow harder, we have increased the frequency, and we have seen that in the process of increasing the frequency to create another node, another antinode is going to be created, because we cannot have a node at the open end. So what is therefore happening here? So we have now a quarter of a cycle plus another quarter of a cycle plus another quarter of a cycle, giving us 3 quarters. So it is right for me to say that the length L is now giving us 3 over 4 of a cycle, or 3 over 4 of wavelength, because the distance between a node to a node is half a wavelength. Then when I add a node to an antinode, is a quarter of wavelength. Half plus a quarter is 3 over 4 wavelength. So if I try to find, of course, lambda will be equal to 4L divided by 3. And the frequency is going to be equal to V over lambda, which will be equal to V divided by 4L. The 3 goes up. So the frequency is equal to 3 into V divided by 4L. Remember, we have seen that F1, which was the same as F0, was V over 4L. So it's like To find the new frequency here, we have got 3 and we have multiplied it by f naught. So it's like we have skipped 2 times f naught. We have moved from 1 times f naught to 3 times f naught. That's why we call this the third harmonic. But like I said, the terms harmonic and overtone may not always be used in this Cambridge curriculum, but other curricula may be using them. So this frequency will therefore be called F3. We have skipped F2 to that effect. So if L equals to that, we have seen lambda will be that. When I try to find the frequency, we have seen that the frequency therefore becomes 3V over 4L. And if we compare F3 with F naught, remember F naught was V over 4L. That was the fundamental mode. So if we compare, we notice that F3 is equal to 3 times V over 4L. In other words, F3 is 3 times F naught. Suppose we even blow harder onto the open pipe, or we blow harder to the open pipe to increase or to produce another higher overtone just above this. In other words, we want to introduce another node. I also want you to see that we have two nodes and 2 antinodes. Initially, we had 1 node and 1 antinode. Okay. So suppose we increase the frequency even harder or even higher, so that we now have another node. In the process of creating another node, another antinode is created. So in the same length, we have now created another node. So initially we had 1 node, we introduced the second one, now we have introduced the third one. In the process, we now have 1, 2, 3. So we have 3 nodes and 3 antinodes. By the way, I want to say that for a closed pipe, the number of nodes is always the same as the number of antinodes. That is very important. The number of nodes is always the same as the number of antinodes for an open pipe. We should note that very carefully. It's not by coincidence. Let's try to see what happens to the frequency in this case. So in this case, the frequency, since L is going to be a quarter plus a quarter plus a quarter plus a quarter plus a quarter, this is 1, 2, 3, 4, 5 quarters. So it's like in this case, we have 1 cycle plus a quarter, or 5 quarters, which is 5 over 4 lambda. So in the same length L of a pipe, we have 5 quarters of a cycle, or 1 and a quarter cycle. So this means wavelength is going to be lambda, yes, the wavelength is going to be 4L divided by 5. And if I try to find the frequency, it will be V divided by 4L, the 5 goes up. So it's like the frequency here is going to be 5 into V divided by 4L. And this is the same as 5 times F naught. So it's like we have skipped 4 times F naught. We have moved straight to 5 F naught. So it's like we now have this as F5, which is going to be 5 times F naught. So what has happened? We skipped 2 times F naught. We have now skipped 4 times F naught. So it's like the even numbers are skipped. So we are only having odd numbers in this case. So the length L is equal to 4 over 5 lambda, and we have seen what lambda is. And from the general wave equation, we have been able to find a frequency F5, which I'm going to call F5, to be 5 times V over 4L. This is why we call the 5th harmonic. However, it is called the second overtone because it is the next higher frequency than the fundamental, but it is the 5th harmonic because it is the 5th. It's like the mode of vibration gives us a 5 over, or it gives us 5 over 4 of the wavelength, or 5 quarters, if I'm to put it like that, 5 quarters of a wavelength. So this is called F5. So the particular frequencies at which stationary waves are obtained in the pipe are called resonant frequencies. Remember, frequencies in a stationary wave, only specific frequencies form stationary waves in a pipe. And these frequencies, like I said, we call them resonant frequencies. So the resonant frequencies in a pipe depend on the length. This is now very, very important. The resonant frequencies in the pipe depends on the length. Even on a string, we saw that it also depended on the length. So it depends on the pipe, on the length of the pipe, and of course the speed of sound in air. However, in general, the length is going to be equal to n times a quarter of wavelength, where n is just only going to be an odd number. If you recall, you note that very carefully. The first one we had L was equal to, for the first one L, I think L was a quarter of a wavelength. For the second one, L was 3/4, I think, of a wavelength. And the third one, L, was 5/4 wavelength. So it's like in general, L should be equal to N times a quarter of a wavelength. So for a closed pipe, L is N times a quarter of a wavelength in general, where N must only be odd numbers. N must only be odd numbers. The number 2, if we look at the frequency, in general, Fn of the nth mode of vibration is going to be given by Fn equals to 2n minus 1 times F naught, where 2n minus 1 is an odd number. If you want to use n equals to 1, 2, 3. If I don't want to use n equals to 1, 2, 3, then I can simply say Fn is equal to n times F naught, but this is not going to be the same as that for a string, because here n will only be odd numbers, only odd numbers. If I want to use n as a natural number, then I would use Fn equals 2n minus 1, because 2n minus 1 gives me an odd number, where when n is 1, then I get f as f1. When n is 2, f2 would be equal to 4 minus 1, which is 3. Now that would instead be f3, but it is better we use just this one here for a closed pipe. Fn is equal to n times f naught, where n is going to be only an odd number. So this is the best way to understand the frequencies formed in a closed pipe. So I think that is for a closed pipe. Let us also talk about an open pipe. Let's see the modes of vibration in an open pipe. So an open pipe is one which is open at both ends. For a closed pipe, it is closed at one end. For an open pipe, both ends are open. So when air is blown at one end of the pipe, a progressive wave travels from that end to the opposite end, where it is reflected on encountering free air. So if a progressive wave is sent from this end, there is a free air at this end. So it will propagate through the pipe until encounter free air and undergoes reflection on encountering free air. So the incident and reflected progressive waves superpose to form what we call a stationary wave. So the examiner will ask you to explain how a stationary wave is formed in an open pipe. When air is blown at one end of the pipe, a progressive wave travels from that end to the other end, where it is reflected on encountering free air which is not under pressure. So the incident and the reflected progressive wave superpose. Remember, they will have the same speed, same frequency, same amplitude, but they will only be moving in opposite directions. So they will superpose, and this will result into stationary wave. So what is the impact here? So the stationary wave is such that a displacement antinode exists at both ends. Because both ends are open, there will always be an antinode there will always be a displacement antinode at both ends. Because at both ends there is a free air, there is a free room, the pressure at both ends is low, is minimum. Therefore, particles or air particles at those open ends can vibrate with the maximum amplitude easily. But of course, between the two antinodes, we expect there to be a node. Between two antinodes, you cannot have two antinodes next to each other when there is no node between them. So between two antinodes, there will always be a node. So let's investigate the first mode of vibration for an open pipe, which we are going to call the fundamental mode. So for the fundamental mode, we have only two antinodes. So we expect a displacement antinode on each side of the open pipe. So in the process, we shall have a displacement antinode at the open end, another displacement antinode on the other side, and in between them there will be a node where particles vibrate with minimum displacement, or they are almost at rest at that point. So that's where we have the node. These animations are just good enough to show you how the particles vibrate, and the vertical lines are showing the movement of the particles, and you are seeing that the vertical lines are moving parallel to the direction of to the axis of the tube. They are moving along the axis of the tube, parallel to the direction of propagation of the wave energy. So in this case, therefore, we have a quarter cycle plus a quarter cycle, which gives us half a cycle. So in this case, in the fundamental mode of an open pipe, we have a quarter cycle and a quarter cycle. I want you all to start noting that we always have one antinode more than the number of nodes. The number of antinodes is always one more than the number of nodes. Yet for a closed pipe, the number of nodes and the number of antinodes was always the same. So here we are seeing whenever we have two antinodes, we have a node in between. So there is always one more antinode as compared to the number of nodes. So here a quarter cycle plus a quarter cycle, it gives us a half. So the length L is giving us a half of a wavelength. So it means the wavelength lambda is going to be twice L. And this means if I try to find the frequency from V over lambda, frequency is going to be V over 2L. This frequency is going to be called the first mode of vibration, which is the same as the fundamental frequency, which is going to be V over 2L. So this is going to be the fundamental frequency. So L is equal to that, and then it gives us the wavelength as 2L. And if I try to find the frequency, we have seen that the frequency F0 is going to be equal to V over 2L for an open pipe. And I'm saying that this is the fundamental frequency, which we can call F1 equal to F0, which is V over 2L. So remember, to increase the frequency, we have to blow even harder into this pipe. So let's try to increase the frequency. So in increasing the frequency, we have to create another node. And in the process of creating another node or more loops, in the process of creating another node, it means we are going to create another antinode, because there will always be one more antinode than the number of nodes. And there are always antinodes at both open ends. So to increase the frequency, if we increase the frequency, then we would have something like this, where we shall have a displacement antinode at open end, something like that. So this is a quarter cycle plus a half a cycle plus a quarter cycle. So a quarter plus a half plus a quarter, I think that is one complete cycle. So it's like the length of the pipe is going to give us a full cycle. So this is what we shall be having in that case: a quarter plus a half a cycle plus one complete cycle. Now some people will say this is a full cycle. The green line could be representing an incident wave. The blue line could be indicating a reflected wave, and these two are meeting to cause superposition. So don't think that this is a complete cycle, because they are looking as if it is a circle. Because if I draw a vertical line through this, you notice that this is half a cycle. One loop is equal to half a cycle, because a full cycle, you can see the animation here. The reflected and the incident wave keep oscillating in that nature. So when I write one loop of a cycle, this is a complete cycle. That is a complete cycle. So if I put an envelope around it, or to show that there's a reflected wave, it becomes something like that. So you can't say that this one loop here is a complete cycle, not at all. So this is half a cycle and half a cycle, because remember, this is a stationary wave. Do not confuse this with a progressive wave. Okay, so in this case, we have a half plus a quarter plus a quarter. I think those are 4 quarters, which gives us a full cycle. So it means the length L is giving us a full wavelength, or a full cycle. So using F equals to V over wavelength. So F is simply going to be equal to V over L. Remember the fundamental that we have had, we saw that the fundamental was F naught equals to V over 2L. So how are these two related? I have to multiply the fundamental by 2 to get the first one. So it means the first one, so F2 is going to be 2 times V over 2L, which is going to be 2 times F naught. So it's like the second mode of vibration is twice the fundamental. So this is what I've been just talking about. The second mode of vibration is twice the fundamental. So the first overtone in an open pipe, which is the second harmonic, is simply twice. Its frequency is going to be twice the fundamental. Suppose we increase this even further. So we increase this even further so that we have a second overtone. So increasing the frequency, then this gives us increasing the we had initial 2 nodes. If we introduce another node, then another antinode is going to appear. So we are going to have something like this. Maybe that is the incident wave. And maybe that will be the reflected wave. So this is a quarter plus a half plus a half plus a quarter. So this is 1 cycle plus 2 quarters, which is 1 cycle and a half. 1 and a half. 1 cycle and a half, which is 3 over 2 of wavelength. So this is what we have in that case. We have 2 halves, which give 1 cycle, and 2 quarters, which give half a cycle. So it means the length L is going to be 3 over 2 of wavelength. Or you can look at it as 6 quarters. A quarter plus a quarter plus a quarter plus another quarter plus a quarter. So these are 6 quarters. 1, 2, 3, 4, 5, 6. 6 quarters, which gives us the wavelength as 2L over 3. And when I use the general wave equation, I'm able to get the frequency F3 as 3 times V over 2L. And of course, this means the frequency F3 is 3 times F naught. So what does this mean? We saw F1 was equal to F naught. We saw F2 was equal to twice F naught. By the way, this was 1 times F naught. We have seen F3 is 3 times F naught. So what does this mean? It's as if it is giving us the same equation as that for the pipes without giving any specific condition. So all harmonics are generally obtainable in an open pipe, just like on the string that we saw earlier on. So we can use the equation Fn equals n F naught, where n stands for the nth harmonic, but n can be any number starting from 1, 2, 3, 4, and so on and so forth. And that also means L is also going to be equal to n times a half of wavelength, where n can be any number starting from 1, 2, 3, and so on and so forth. So the same equation we use for a string, waves on a string, is the same equation we can use for waves in an open pipe, waves on an open pipe. Okay. So that is how we derive these harmonics. So I want you to compare. If I use Fn equals to n F naught for a string of one open pipe, n can be 1, 2, 3, and so on and so forth. If I use the same equation for a closed pipe, n must be only odd numbers. That is going to be very, very important. Okay, let's see how we can obtain or if we can demonstrate stationary waves using microwaves. For my students in the class, you are supposed to watch this video here. Just click on or just paste this you can paste it into your browser or into your YouTube and watch the video of demonstrating stationary waves using microwaves. All waves can form stationary waves. All waves can form stationary waves. So for microwaves, we know that these are electromagnetic. So let's have a source of microwaves, such as this one here. So remember, for stationary waves to be formed, we must have the incident and reflected wave. So a source of microwaves is placed facing a reflector. We need something which is going to reflect the microwaves. Then a small detector is placed between the source and the observer. So I have a detector here which is connected to a microwave detector. This is a microwave detector somewhere here. So a small detector is placed between the source and the reflector. Then the reflector is therefore going to be moved between, either the reflector is moved towards or away from the source until the signal picked up by the detector starts fluctuating regularly or fluctuates regularly. That is, the detector may detect a maximum followed by a minimum, a maximum, a minimum, and so on and so forth. So we move the reflector towards the source or away from the source until the signal which is noted by the detector starts fluctuating. In other words, it becomes maximum, and if we continue moving, it becomes minimum, and if we continue moving, it becomes maximum, and so on and so forth. Alternatively, we could fix the metal plate or the reflector and the source and move our detector between the reflector and the source to detect those points. If they are not there, then we have to adjust the distance between the reflector and the microwave as before. So the minima are going to be the nodes, or the point where the signal picked by the detector is minimum. That is the point where we expect the nodes to be of the stationary wave pattern, and the maxima are going to be the antinodes. So if we detect positions where the signal detected by the microwave detector is minimum, then it becomes maximum and it goes back to minimum, then we know that a stationary wave has been formed because the minima corresponds to the nodes and the maxima correspond to the antinodes. So the only thing that remains is now for us to measure the distance between the corresponding distances or positions of minima and the maxima. So measure the distance moved by the detector between adjacent nodes or adjacent minimum points or adjacent antinodes. So of course you can't measure the wavelength directly from the graph. You can note that I detected a minima here. The next time I detect a minima, I measure the distance between these 2 points. Call this distance d. Remember, we saw that the distance between a node and another node was equal to half wavelength. The distance between a node and the next node was half wavelength, or the distance between an antinode and the next antinode was half wavelength. So now I can determine the wavelength. So measure the distance moved by the detector between adjacent nodes or adjacent antinodes. This distance is half wavelength of the microwaves, which means the wavelength is twice the distance between adjacent nodes or antinodes. So the wavelength is going to be 2 times the distance between the node and the next node. So if this distance is measured, maybe using a ruler, and that distance is d, then the wavelength is always going to be twice that distance. This point is very important, especially in calculations. Do not forget to watch the solved past paper questions to understand this concept in more details. Can we therefore measure the speed of sound using stationary waves? We have seen that we can measure the wavelength of microwaves, for example, using stationary waves. Can we also measure the speed of sound using stationary waves? Of course, yes. So the principle of resonance in a tube closed at one end can be used to measure the speed of sound in air. For example, if we get a glass tube and place it in a cylinder of water, and we try to raise the tube. By raising the tube, the length of the column of air in the tube can be increased if we raise the tube. And if we were to place a tuning fork above a vibrating tuning fork of known frequency is held above the open end of the glass tube. Of course, this causes the air in the tube to vibrate. And because the air column length can be changed, then it means the frequencies of vibration can also be changed. So the tube is gradually raised, increasing the length of the air column. At a certain position, the note becomes much louder, and when we notice a point of much loudness, that is maximum amplitude, then we know that resonance has occurred. So this is known as the first position of resonance. The moment we hear the first loudest sound, that is going to be the first position of resonance. And it occurs when a stationary wave corresponding to the fundamental mode is established inside the pipe. So when we hear the first resonance, we know that a stationary wave which corresponds to the fundamental mode of vibration is formed. And therefore, the only thing that we can do is to measure the length L, that is the length of the air column in the pipe. Then we can raise the tube even further. The tube is raised further until a second resonance position is found. This corresponds to the second mode of vibration, and then we can find the length L2 at this position, and then we can use these two lengths to be able to determine the speed of sound in air, because what is in the pipe is actually an air column. So this is what I've been talking about here. We have an open pipe which has been dipped into water, so it is now going to the water at the other end will act as a closed, it will act as if it is closed, it is making the pipe to be a closed pipe. So we place a vibrating tuning fork on top of the air column as we raise the tube. So if we hear the first loudest sound, we know that the first resonance has occurred. So the first mode of vibration for a stationary wave has been formed in the air, which is inside the open pipe. Then we measure the length L1. Then we can raise the tube again until we hear the second loudest sound, which means the second position of a stationary wave has been established, or the second mode of vibration of the stationary wave in air inside the pipe has been established. So we measure the length there. Remember, we have seen for the fundamental mode, L1 is equal to a quarter of a wavelength. And for the second mode of vibration, we saw that L2 in this case is equal to a half plus a quarter, which is 3/4 of a wavelength. So if L1 is measured and L2 is measured, then we can find the wavelength. So the two resonance positions are illustrated in this diagram. At the first position of resonance, L1 is a quarter of a cycle, and at the second position of resonance, L2 is 3/4 of a 3/4 of a cycle. Then if I do mathematics and subtract the two equations, subtracting the two equations, say L2 minus L1 gives me an expression lambda being equal to twice of L2 minus L1, because when I subtract 3 lambda over 4 minus lambda over 4, this gives me 2 lambda over 4, which is simply lambda over 2. So if I use the general wave equation, V equals to lambda times F, then it means since I know what the wavelength lambda is, being equal to 2 times the difference in the length, then I can find the speed from V equals to twice F into L minus 1. So this will give me the speed of the sound in air. So in that case, the speed can be calculated. Do not forget to watch the solved past paper questions to be able to use this concept. A few things we need to note about this method of determining the speed of sound in air. I want you to observe that a node is always formed at the water surface, because the water surface acts as if it is causing the pipe to be closed at the bottom end. And number two, when a loud sound is heard, the frequency of the sound equals to the frequency of the tuning fork being used. Whenever resonance occurs, two frequencies are matching. That is, the frequency of the tuning fork is matching with the frequency of the air molecules which are inside the pipe. That's why we hear a loud sound. That's why we call it resonance. So whenever we hear a loud sound, it's because the frequency of the tuning fork is the same as the frequency inside here. So if we know the frequency of the tuning fork, then it means we know the frequency at which the loud sound is heard. The only thing we need is to measure the length. Alternatively, we would have used a tube with a tap at the bottom. So instead of raising the tube, we could instead pour water into the tube and have a tap. So we just open the tap while holding our tuning fork on the top. When we hear a loud sound, we close the tap and measure the length. So in this case, the length of the air column would be increased by gradually opening the tap at the bottom and reducing the water in the tube, giving the same, and this would give the same results. It would give entirely the same results. Okay, can we also measure the wavelength and speed of sound using sound waves in just a free air rather than in a pipe? Of course, yes, we can still do that using a loudspeaker. So let's see measuring the wavelength and speed of sound using stationary waves in free air. The other one, we use the pipe. Let's think of a situation where we have free air. Just like we have done with the microwaves, we can still find the wavelength and the speed of sound using stationary waves in free air. To create a stationary wave, we need a reflector and we need a source of waves. So here, the source of waves is the loudspeaker. So this is the source, which is connected to a signal generator. Let us assume that the frequency can be determined by the signal generator because the signal generator adjusts the frequency of the wave. So the frequency F is known. So the waves, a progressive wave is to be sent from the source up to the reflector. And the reflected wave is supposed to leave the reflector back to the source. And the process continues because there's a continuous production of waves from the source. So these two are going to be superposing between the source and the reflector. So we have a detector of these waves, which is most likely going to be a microphone that converts the sound waves into an electrical signal, which can be displayed on the screen. So the signal generator and the loudspeaker produce a note of known frequency F. And the reflector is moved slowly back and forth until the trace on the oscilloscope has zero amplitude. So when we move the reflector back and forth and we notice zero amplitude on the screen, then we can mark that point. So where we have zero amplitude on the screen, it means a node has been traced or a node has been created. So when this happens, a stationary wave has been set up with one of its nodes in the same position as the microphone. So here there will be a node. A stationary wave has been formed. When we see that the reading on the oscilloscope is showing a horizontal line which shows 0 amplitude, then it means we have reached a point where a stationary wave has been formed with a node at the position of the microphone. Now that the microphone is not picking vibrations here. Then now we can move the microphone. Now that we know that this is a node, we now move the microphone either towards the source or away from the source until we detect the next position where again the amplitude here becomes again 0. So the microphone is now moved along the line between the loudspeaker and the reflector. The amplitude of the trace, of course, goes to maximum because we have seen there is a node at the position of the microphone initially. So the amplitude of the trace on the oscilloscope will increase to a maximum and then decrease to a minimum or 0 again. If we were moving it towards the reflector, now it is in this position here. This is the new position where we notice that again it goes back to 0. So this is going to be the second node. So what do we need? We just need to measure the distance between these two positions, which is going to be the distance between the nodes. So the microphone has been moved from one node through an antnode to the next node. So between two nodes, we expect there to be an antnode, of course. Because if we initially noted a node at this point here, and we move the microphone, and we notice that the reading here increases to maximum and so on and so forth, and then it goes back to 0. So it means we have moved it through a node, an antnode, to the next node. That's why the reading on the c.r.o goes back again to 0. So we have detected another position for the node. So the remaining thing is going to be to measure the distance. Measure the distance d, which is between the two positions, that is the adjacent nodes. You could also have considered antinodes. Remember, the distance between two adjacent nodes is half wavelength, which means now we just multiply that distance by 2 to get the wavelength. Do not forget to watch the solved past paper questions to easily understand application of this concept in more details. Then using V equals lambda times F, of course, since we know the frequency of the signal generator, we have seen that the wavelength is twice the distance between successive nodes, or twice the distance between successive antinodes. We just substitute and obtain the speed. So the speed will be twice 2 times F times D, because the wavelength itself is twice the distance between the two nodes. This concept is very, very important in calculations. I think let lesson 9 stop here. I don't want it to be long because it was supposed to be long since I was going to do examples. Let me do examples of stationary waves in pipes in lesson 10.